Now let's discuss electromagnetic waves. This sounds daunting, but really this is just a big word for light. So light is a wave. Let's consider the anatomy of a light wave. Since it's a wave, we know it must oscillate, so we can represent it by a sine curve like this. So in a mechanical wave, such as a water wave, we know that the wave consists of course, water, and in the wave on a string, it's made of the string. So a light wave instead, what could this be made of? We'll get a hint from the name of it, electromagnetic wave. The electro part is for the electric field. Let's say this is our electric field, which oscillates between some greater strength and a lesser strength. But it isn't quite so simple. There's also the magnetism aspect. There's a second component of the electromagnetic wave, which is perpendicular to the electric field, and that's the magnetic field, which also oscillates. Here's a much better picture. You can clearly see the perpendicularity between the electric field and the magnetic field. Since light is a wave, this means that it transmits energy across space. We know that this is true because when you sit out in the sun, you get warm, and if you sit out in the sun too long, you get a sunburn. Something special about light as a wave is that it can radiate, which means that it can travel through space when there's no matter. A water wave requires water in order to move, because the water particles have to bump into each other to create the wave action. And a wave on a string is similar. In a string, the tension forces caused by the particles next to each other along the length of the string cause the wave to propagate. In an electromagnetic wave, however, there's no matter for these forces to exist in. Nevertheless, light waves can still travel through matter, which is why you can see light through your window. That's all for now.